Part 1, CPU bytes, instructions, data, foundations. For question 1, what is the difference between data and instructions? At the hardware level, there's no difference. Both are just bytes in memory. The distinction comes from how the CPU interprets them. Instructions byte fetched via the program counter and decoded by the CPU. So that's why there's huge cost to decoding in CPU pipeline. Data bytes read via load or store instructions, and this data only comes once we fetch the instructions. In program counter, we fetch instruction, not data. So some of those instructions have dependencies outside in the memory that needs to be loaded by program counter. It could be from the L1 cache, L2 cache, L3 cache memory, or on the disk. What makes something code is control flow. PC moves through it. That's also the reason why PC or program counter execute it incrementally. What makes something data is being referenced by an instruction. So the instruction code or the code stream we discussed in the previous chapter will execute this data that is being referenced in the memory. Can a CPU execute data? Yes, if the PC jumps to that memory address. So that's where you get this pointer chasing or the data inside that instruction lends to another data that produce like a dependency. That's exactly why the serialization vulnerabilities exist because some data execute like instructions or functions which or methods which should not be the case. Example, JSON or message pack is supposed to be data. If decoded into objects that trigger behavior, code execution risk. This is why data should never be executable if it's a security rule. What is the program counter? The PC is a register that holds the memory address of the next instruction. Flow, PC to fetch bytes to decode to execute to PC advances. So again, the PC is a register that holds the memory address of the next instruction. The flow, you start from PC to fetch bytes to decode by the CPU execute and then the PC advances. So it's just a register that holds the memory address of the next instruction, and this is actually the start or the front end of our CPU pipeline. What is a pointer, really? A pointer is just a memory address stored as data, not an index, a sequence, but the address where something lives. Example, char asterisk name equals 0x7FFE1234 semicolon. Basically, we're pointing to an address where a data lives or where something lives. Let's say we're trying to reference something, whether it's instruction or data. So this is where the pointer chasing means. Pointer chasing equal following an address. And then if you get a cache misses, it's slow. Part 2, pipelines, prediction, RLE, column stores. Why do CPU predict? Because waiting is expensive. Branches break pipelines. Memory is low, so CPU guess, branch prediction, prefetching. If wrong, pipeline flush, performance hit. If right, massive speed up. Is this related? to run length encoding? Conceptually, yes. Both exploit patterns. Branch prediction predicts control flow. RLE, or column storage, exploits repeated values. Example column USA, 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 stored as USA, 4, less memory, better cache locality, faster scans. How is this different from row-based storage, B-trees? Row store, B-tree, node to pointer to node to pointer to row. Pointer chasing, cache misses. Column store, length value. Sequentially, CPU friendly, vectorized execution. This is why analytics engines love column stores. Part 3, JSON message pack, length prefixes. Why is message pack faster than JSON? Because it is binary, length prefix, sequential. JSON, open semi-curly bracket, quote username, colon, quote Martin, closing semi-curly bracket. With message pack, we have 8, quote username, the next 6, quote Martin, no pointers, no parsing strings. So you can see in JSON, you still need to parse the strings and the spaces. For message pack, no parsing strings, CPU reads sequential bytes because it's stored as it is in bytes sequentially that has like a format for message pack that it allows it to store the bytes sequentially instead of like porting to another part of the storage or memory. So it doesn't have that pointer tracing where you need to point something where the memory where something lives. Is column storage like message pack? Yes, philosophically. Both avoid pointer chasing, use length prefixing, favor sequential access. Difference: message pack equal transport format. Column store equal query execution format. Part 4, databases, bytes, the main objects. What are the main objects? They are in-memory representations of real-world entities. Example, Postgres slash Supabase, select ID, username from profiles, becomes in-memory. Struct profile, open semi-curly bracket, next line, int ID, semicolon, next line, char asterisk, username, semicolon, next line, closing semi-curly bracket. These are data, not instructions. Does PostgreSQL store instructions or data? Only data. Instructions live in the Postgres binary. So the Postgres has this binary format where it stores the instruction, but the actual PostgreSQL only stores data. Tables are bytes in disk pages. So the table that you create are just bytes in these pages. So the data that the actual user created becomes like a data, and the SQL um, logic becomes the instructions. That's where that's what's posted in Postgres binary. Indexes are structured bytes. So again, indexes are structured bytes. So the structure index, since we use index to structure data, whether it's storage engine like in LSM3, or whether it's B-trees, it's just a structured bytes or structure organization of the data that the user like enter in there. For example, logging up. CPU executes Postgres code to interpret data, not execute it. So then the CPU will execute that instruction in the binary to interpret that data, not execute it. So how do bytes and then that transformation of data will then be received via your back end or the state because in this case, for example, on my blogging Flutter blogging app, the back end in the UI perspective or the Flutter perspective is just the Dart. It controls the business logic. It's not the UI that responsible for the design or the color or what you see on the HTML or in the website, but it is also responsible for the actual logic. So that's a different state. Now that is actually a front end, just a front end to Supabase, and then Supabase is just a front end to PostgreSQL. So that's basically happened, and then PostgreSQL interprets the data that and then execute something and then transform it and return back to the register, return to the Supabase, and then return to the application logic and then to your UI. How do bytes from get from disk to CPU? So we have disk to OS page cache, to Postgres buffer cache, to CPU L3, to L2, to L1, to registers, to execution units. No malloc for disk reads, mmap or OS buffers are used. Part 5, front end to back end to database end to end. Does JSON travel via TCP or UDP? HTTP is always TCP, not UDP. So flow reacts to fetch function to browser runtime to OS system call to TCP to Supabase API. 14. After Supabase API, of course, it will contact the PostgreSQL and that will contact disk to memory to L3 to L2 to L1 cache. The CPU will transform the data, return back to register, and then flow to the memory, and then get back to the Supabase API. Now, who parses JSON? Client parses response JSON. Backend parses request JSON. UI components never parse raw JSON, the runtime does. Is backend a client? Yes, from the database perspective. Perspective matters. Browser equal client of Supabase. Supabase API equal client of Postgres. Postgres equal the server. Providers, Redux, Riverpad, Firestore. What is provider? A controlled access point to state or logic. It owns states, notifies dependents, abstract data source. How is provider similar to Redux? For Redux, global state tree, provider or riverpad decentralized state. Redux reducer, provider or riverpad providers. Redux time travel, provider or riverpad reactive caching. Redux single snapshot, provider or riverpad per provider snapshot. How does Firestore on snapshot work? Persistence connection with socket or long polling. Server pushes diffs, so it's kind of like the riverpad. It's decentralized state. It pushes diff kind of like with React. So it's similar to one snapshot of the Firestore client updates in memory state, and then the UI reacts. So it updates the cache in memory for that. IndexedDB is the local persistent, not the source of truth, just like Redux is the normalized data, not the source of truth, which is the PostgreSQL. The Supabase do the same thing, yes, via real-time subscription. Supabase, I think the Supabase, let me see, is, yeah, so the Supabase implement on a state change that listen argument data. Supabase listen to Postgres while pushes row level changes. Client updates providers or state. Is business logic always backend? No, business logic can live in backend SQL constraints, triggers, front-end state, Redux, Riverpod shared logic, TypeScript, or Dart. So, like, your backend is kind of like the Supabase. So you use that decent, like to contact that, and Supabase use TypeScript. So stateless logic, when it encodes rules. Summary, one sentence answers you should memorize. Pointers are memory addresses, not indexes. Column stores avoid pointer chasing. JSON is data. The serialization box makes it dangerous. CPUs predict to keep pipelines full. Providers are controlled state gateways. Databases store bytes, not objects or code. Everything becomes sequential bytes eventually.